start. There is a lot of room here. For some reason, people are afraid to sit. This is a very privileged location, and everyone is welcome to join. Irrespective of your seniority, we would be delighted to have you around here. One general announcement: we will have a photographer taking a picture, a group photo of all of us. It's a nice day today, and that will happen at 1:30 when we finish this session. And also, at the same after that group photo is taken, if anyone wants to get a personal photo, that will also be possible because we have to update. How do you call it, Mark? Our Facebook or whatever. There is a place where we put individual photos near the ITC entrance, and so anyone that wants to get a personal photo updated, because you look better now than you used to, that's an opportunity. Okay, so we have a number of, we just had an excellent colloquium by Dan Paul, I don't know if he's here. Oh, here you are! You showed up from the back. Okay, that was wonderful. So we haven't heard about a new type of source other than black holes or neutron stars, but Dan says that under the noise there are some strange things. Maybe if we wait another year or two, they will roll into the high signal to noise regime simply because the nearby universe is Euclidean, and therefore there should be some very loud events of the same strange type closer to us. So we just need to be patient. That's all.
I don't have to give my talk.
I just summarized the highlights. Okay, so we have a number of interesting presentations. We start with Donzi Lee. She's a visitor from Caltech, and she will talk about the recent progress in puzzle of fast regulars, an unsolved problem in astrophysics.
Hi, I'm Donzi, and I thought I do, but you cannot hear me. Is that the angle or something? Haha. Is that working? Oh, okay. I'll just speak loud. Hi, I'm Donzi, and it is my honor to share about some interesting new studies and puzzles about fast radio bursts. So I guess probably everyone has heard about fast radio bursts. It's bright, very short duration radio burst of extremely high energy. And the right panel is the real image of the first fast radio burst detected. The x-axis is time, the y-axis is frequency, and the black swing is the burst. And in the radio frequency, the signal from different frequency arrive at different time, and this time delay is telling you how much electrons it has encountered in the way. So because it can tell you how much electrons it has gone through, and it's coming from a cosmological distance, so it's kind of considered as a promising probe for cosmology. And its first detection is at 2007, so it's a relatively young field thanks to the progress in the fast processing and GPU and etc. Now we have more bursts and we have more understanding about FRB progenitors. So around 15 years later, we know lots of things about, for example, the highest energy so far we're seeing, and the sky rate. And also there's some direct evidence that's coming from very small detection of bursts, but from special sources. One is the discovery of first repeater, and that tell us not all the FRBs are from catastrophic events. And the second one is pretty recent, 2 years ago, the detection of FRB burst from a galactic magnetar. And it shows that at least the magnetar can produce FRB burst, and at least some bursts might be coming from from magnetar. So now what's the current status of FRB? We have more than 600 published bursts, especially thanks to the CHIME telescope, which has 1,024 beams searching the sky all the time. And we published more than 500 bursts last year. So now really it's the time first to think about cosmology again, and also think about moving forward what kind of observation will be helpful, because like it's difficult to improve understanding with single detection of field burst. For example, for progenitor, whether all FRBs are coming from magnetars, and also thinking about cosmology, like whether we need more information about the circumburst environment so that we know how much it will bias the cosmology detection. And in this talk, I'll review a few of the puzzles from the recent studies. The long-term periodicity, the local environment of FRBs, and some magneto environment of FRBs. And these are the nice puzzles because they're not directly related to the emission mechanism or something which may or may not be solved, but they're more like the puzzles to the progenitor or the nearby environment itself. So one thing is, the first one is the long-term periodicity. So 2 years ago, I have found a 16-day period from an active repeater in the CHIME sample. So this is the burst arrival time folded as 16 days. And the y-axis is different cycles. You can see from now it's like 4 years, and they're strictly still following this 16-day period and arriving at only 1/3 of the total phase. And I couldn't find a p dot still, like so the p dot has to be smaller than 1e minus 4. So shortly after this, like tons of theoretical model has been proposed, but you can summarize it into either it's from orbit or precession or spin. So for the precession and spin, like it is non-trivial for magnetar to slow down to 16-day period, and also it's non-trivial for it to preserve the free precession. So the other idea is you can have a companion to orbit with it, or you have a companion to force it to precess. So it really, either we have to improve our understanding of magnetar, or it has a companion. So, and the second puzzle is, like, last year, there's the fast radio burst. Oh, well, first of all, there are like order of 20 localized FRBs, and it seems that it's localized to all kinds of hosts, not tracking star formation, not tracking stellar mass, and not tracking anything at all. And then last year, there's a fast radio burst localized to a globular cluster. So this is the galaxy, but this is where the fast radio bursts are localized, really away from the outreach and in the globular cluster. This is striking. First of all, like the globular cluster hosts old stellar population. It's really difficult to expect it to have a young magnetar from the supernova remnant, from the burst of massive stars. And the second thing is, even if you consider the dynamic channel, so like the most abundant one is the white dwarf merger, but even you assume all the Chandrasekhar white dwarf merger are can generate a new magnetar, it can only account for 1% of the magnetar compared to the total magnetar in the galaxy. So but this burst is really the most nearby fast radio burst we detect so far out of our galaxy. So if only 1% of that can be from globular cluster, it will be surprising why the closest one is from the globular cluster. Because further away, we don't know whether it's from globular cluster or not. So it's surprising and kind of uncomfortable. And the third thing is the recent increased study of the magneto environment of fast radio burst. So some of them has really high RM. So RM is the integral of electron density with the parallel magnetic field, which basically tells you the magneto environment, because the ISM and IgM can contribute very little compared to those values. And the only other object has observed to have such high RM is the one it's the magnetar near the galactic center. It has nothing to do with the magnetar. It's because the supermassive black hole in the galactic center. It's not surprising for it to have high RM, but it's surprising for the FRBs. None of them are actually near the galaxy center. All of them are offset from the galaxy center. And yes, and they not only have very high RM, it's also very, very fast. Like, look at this source. It's even flip signs, like in the time scale of months. And the yellow dots are the galactic center magnetar. It is still changing, but not as drastic, much less drastically than FRB. So it has to have some environment that's extremely magnetized and also extremely variable. And also surprising. So one thing you can think of to introduce the RM is if the FRB is in a young supernova remnant. However, it's even confusing that one of the FRB that you see large RM and you see this large fluctuation of RM, but you look at the localization, it's in the circle of, it's the blue circle. It's offset from the star forming region of the galaxy. So if you naively interpret the age of the object from the distance divided by the characteristic velocity of neutron star, which is 100 kilometers per second, you expect it to be pretty old. So it's sometimes a little bit uncomfortable to think of young supernova remnant. And the other explanation is, again, that maybe it has a companion. Because for a companion, it can be magnetized and it can have much smaller scale variation. And not only about that, so this source also have this RM-like oscillation in circular and linear polarization, which cannot be introduced by RM. It has to go through a region where it's either relativistic or pair plasma or extremely high magnetic field. So this source has to go through first a cold plasma region and to introduce some RM, and then the second like eigenmode linear region, and the third region of cold plasma to introduce the second RM. It's not difficult to have this region close to the progenitor, but it's difficult because it's already away from the progenitor for you to have cold plasma. And then you enter another region which is similar to the environment near the surface of some stellar. And then you go to some cold, which is not difficult. But this region, after this cold region, is slightly weird. Oh. Time stop? Oh, no. Oh, yeah. So what we observed recently is that we observe actually similar behavior in the pulsar. We can see the change in circular polarization in the near the pulsar, and we can explain it with the companion poloidal field for this kind of behavior. And our model matches the data very well. So the dots are the data, and the curves are the model. And we have, so the model is some propagation matrix applies on all spin phase together. So it's the same matrix applied to the spin phase, but we can reproduce the wiggle very well. So we are not optimizing for that. It just naturally matches very well. And also this system has very high rotation measure changes. So it can change by plus minus 100. And from the magnetic strength, we infer from that, actually in the region where it's depolarized, we actually expect few thousand. It's approaching, it can reach very high RM as the FRBs. So it's almost like very similar property between these objects. And our method can be applied to FRBs potentially. And also it suggests that maybe some of the FRBs are in the binary. And as said before, it can explain the offset from the star forming region, the one in the globular cluster because it has more binaries in globular clusters. And also it can explain the long-term periodicity with the companion. And that's, and moving in the future, we can look for more exotic polarization events, and we can look for more globular cluster FRBs to understand the picture of the progenitor better. And thank you.
Obviously, this could be a mixed bag, right? Different types of sources
Yes.
contribute. But the one category that is the at least that there are two types. One is repeating and the other ones do not repeat. And, do you think it's a matter of age? Is there any indication that from their birth sites, those that are repeating are closer?
Yeah, the repeating are definitely closer because the average dispersion measure is lower for the repeating sources. And but it's also probably, if it's not the true category, it has to have some age or something evident because there's some burst property. The repeating sources are wider and narrow bandwidth, so they intrinsically look different too. So they're probably either different groups or evolution effect, which we don't know yet. Yeah.
More questions or comments? Lots of puzzles. It looks like.
Yeah. So which is good. Which means that we are still having abundant things to study for FRBs, and also there will be lots of instruments developing to detect more FRBs and more localization. So it's still an exciting field.
If you had to guess, would you say that magnetars are the most likely origin, or would you say there should be also white dwarf binaries? What is your guess as to the dominant fraction?
So from the fact that we detected the galactic magnetar interpolate the luminosity function, it should be able to explain a significant fraction of FRBs. But from the detection of globular cluster 1, which is definitely not normal magnetars, so there's probably a not negligible fraction from either a different kinds of magnetar or binaries. That's my current feeling. Yes.
Yeah, we will have better statistics. And if we detect gravitational waves, that will change.
Oh, then yeah, exactly. Yes, I think there are efforts to try to cross-correlate, but I think it's slightly currently still in the. Well, I think mainly because the localization of the gravitational wave is not very accurate.
So we can only do it in time.
Yeah.
Which is fine.
Let's thank Gonzi.
Can you hear me all right?
Yeah.
Hi, so yes, I'm Jake. I've just started a postdoc at the ITC a few weeks ago. I'm talking about some of the current work I've been up to, kind of following on from a PhD and kind of feeding into what I'm going to be doing while I'm here. And looking at giant black holes early on in the universe and what signs there are that they exist. So, a bit of background and motivation. There have been now several hundred quasars have been discovered at high redshift, and by high redshift I mean redshift 6 and above. They're generally pretty bright. I guess observational bias will mean that that is what we've found so far. But they have very high luminosities that point to them being powered by very massive black holes in excess of 10 to the 9 solar masses. Even the record holder, the largest we've found so far, has an inferred mass of about 10 to the 10 solar masses, which is kind of interesting in how you get to that kind of mass so far. So these are the very bright quasars early on in the universe. But that means you've got to grow these black holes to 1 billion solar masses, maybe even 10 billion solar masses within the first billion years of the universe, which is difficult. So, for example, if you consider a 1,000 solar mass seed, to grow it to a 10 to the 10 solar mass seed by redshift 6, not seed, redshift 10 to the 10 solar mass black hole by redshift 6, it means you need to accrete constantly at the Eddington rate from about redshift 23 straight through. So it's unclear whether that's a feasible path for black holes to grow. It's kind of, people sometimes invoke super Eddington accretion and other ways of trying to grow these black holes. But there are a lot of uncertainties generally on, how seeds form, where they form, how massive they are, and kind of then how there are uncertainties as well in measuring the masses of these black holes at redshift 6, well, even lower than that, but kind of these very massive black holes, there's probably a 0.3 dex, 0.4 dex uncertainty in their masses at least already. But kind of, this motivates some of the work that I've been doing to find out what other observables might be able to point us in the right direction for these black holes. If you have such beasts, you expect them to have had some form of impact on their surroundings, and they are very bright quasars that have high luminosities, so they're kicking a lot of energy into their surroundings. And so to start trying to answer this question, I've been using zoom-in simulations of kind of one of the largest halo within a reasonably fine 500 megaparsec sized box, so it's from the Millennium simulation originally, which forms by redshift 6 a halo that has about 7 times 10 to the 12 solar mass kind of M200. And so I've been using the Fable galaxy formation model, which is kind of built on the original Illustris model with kind of improved AGN feedback models to try and better match gas fractions at lower redshift, for example. But as I'll show, it's still difficult to get to these kind of extreme masses, and particularly early on with fiducial models. So I've been looking at some of the modifications of those things as well. So the modifications to the model I've been looking at are kind of trying to have models that are not kind of completely a load of crap to start with, kind of reasonable changes to existing models. So we've kind of seeded black holes earlier. It's so uncertain when black holes are seeded anyway. So we seed 10 to the 5 solar mass black holes in 10 to the 9 solar mass halos in this reference model, whereas they're seeded in 10 to the 10.5 solar mass halos later on. In the original Fable model, we reduced the coupling fraction of feedback energy from 10% to 5%. Again, this is fairly uncertain what this figure would actually be in the real universe, so it's a reasonable kind of change that we've made. And we've allowed kind of mild super Eddington accretion up to twice the Eddington rate. And as I'll talk about in a little bit as well, there's another run I've done which has reduced supernovae feedback as well, which has extra impacts. So if I look at the black hole growth curves of these, just for time's sake, I'm not going to explain the blue and red regions, but the pink line at the bottom is the fiducial Fable run. So we seed a 10 to the 5 solar mass black hole around redshift 12, and it grows fairly quickly and reaches about 10 to the 9 solar masses by redshift 6, which is kind of on the lower end of some of these massive quasars, the estimates of mass that we have for them. But if we consider like some of the higher redshift ones at redshift 7 or 7.5, we're lying nearly an order of magnitude less massive than the inferred masses at those redshifts. With the changes that we've made to the model, we kind of seed earlier, so black holes can grow earlier. And the changes we made effectively encourage gas availability and accretion in the protocluster. Effectively, this is, and so that it grows earlier, and you can kind of get to these 10 to the 9 solar mass black holes by redshift 7.5 already, and then reach 10 to the 10 solar masses. So these kind of most extreme examples by redshift 6. So kind of the first point to say is there's enough gas there to grow these massive black holes in massive halos. That is the caveat here. If the kind of feedback conditions are available, if you can get that gas into the black hole. And then the kind of other impacts that this has is on kind of star formation. The AGN doesn't really do a great deal until kind of redshift 8 onwards, roughly. So this is as the halo's growing over time. This is kind of the fraction of stellar mass compared to the expected baryonic mass, aka the dark matter mass times the universal baryon fraction. But by the time we get to redshift 6, even the most extreme models we have in terms of AGN luminosity that grows these 10 to the 10 solar mass black holes, the stellar mass to kind of halo mass ratio is considerably above what you might anticipate. So this is from Baruzzi et al. 2013, this redshift 6 stellar to halo mass relation, which is extrapolated, and then you kind of have to extrapolate it to even larger masses to kind of look at where these might be. But we have a lot of stars, perhaps more stars than we would expect to have. So if this kind of relation is accurate, we might need even more kind of feedback and reduction of star formation to be able to come onto this line. And so another point is that future kind of high redshift measurements of the stellar mass function will be able to kind of constrain when feedback kicks in, particularly from AGN and black holes. And so let's have a look at kind of some of the kind of the actual maps of those areas. So the kind of the top left here, we have a run with no AGN at all. Black holes are completely switched off, compared to the fiducial Fable run on the top right, and then these reference runs with reduced supernova feedbacks bottom right and not on the left. There isn't a ridiculous amount of difference. This is within the virial radius, I should say. So this is fairly close into the halo. Well, depends who you ask, I guess, whether this is close in or not. But kind of even the fiducial Fable run doesn't have a huge impact. When you start to go to the reference run, you do start to see the disruption of inflowing filaments compared to the no AGN run. So that's kind of starting to cut off that cold gas supply for star formation that we might expect to see. And we do start to expel more gas into the surroundings. But then we want to kind of look larger scale as well. So this is a metallicity map in the no AGN run. So looking at metallicities at large distances from the quasar, which might be able to be probed with JWST. When we go to the Fable run, there's not much difference. The Fable has not had much of an impact by redshift 6. The standard model does not. Even with a 10 to the 9 solar mass black hole in the center, it's just not had enough time. When we start to go to a 10 to the 10 solar mass black hole, we start to see faster outflows pushing metals out to higher distances. So we have kind of solar almost, or even supersolar metallicities well outside the virial radius of this halo at redshift 6, driven by AGN outflows. But this is quite sensitive. The size of this hot halo is quite sensitive to when feedback kicks in. As I show here, with the supernovae turned down, perhaps counterintuitively, you get more of them. And so you blow out, you can encourage black hole growth a little earlier in a shallower potential well. You blow out metals even further. So these are one way we can start to try and constrain, potentially, if we detect metals at very large distances from the center quasar, we'll start to constrain the past accretion and past impact of these black holes. Now, perhaps optimistically a little, looking at an X-ray map, this is the penultimate slide, so looking at an X-ray map, perhaps optimistically with Athena or Lynx, the angular resolution will be worse than this, but we can start to see kind of a centrally concentrated peak in the Fable run on the left, which starts to be blown out, and the profile is shallower with kind of these gargantuan black holes in the center. And similarly, one thing that might be able to be probed a bit closer, at least with ALMA, for example. While you won't be able to kind of pick out all of the structure in these things, you'll hopefully be able to tell between a kind of very centrally concentrated peak because of very high gas pressures in the center, or a kind of smoothed out, shallower profile when we have these kind of large feedback episodes being pushed out. And so I'll just briefly put my conclusions up. And so we can form these kind of most extreme objects with plausible changes to existing models if you're in a large halo already. That's the kind of the key thing. The gas is there. And so I've been starting to look at what other evidence that we could try and look for to try and see if these black holes have had the impact we might expect them to, and to constrain early feedback models. And kind of future work that I'm working on at the moment is looking at kind of the effect of numerical resolution on top of that. For example, just kind of these two metallicity maps at lower resolution and higher resolution simulations, the kind of morphology of the metals changes quite a bit, and we actually get a lot more cold inflowing filaments coming into the halo. So this is a quasar at redshift 6. If you've got more cold gas coming in theory, that might boost black hole growth further. So this is kind of another thing I'm looking at to see what kind of masses we get to when we have higher resolution as well. So I'll leave it there. Thank you very much.
Just before we get to more questions, it seems like at redshift 6, 7, the highest mass black hole is the same as the highest mass black hole at redshift 0, roughly 10 to the 10 solar masses. And even though I knew this fact for a couple of decades, it was never clear to me why there is a ceiling to black hole masses that is independent of cosmic time. Do you have an explanation of that?
That is a good question. I mean, accretion gets very inefficient and difficult when you get to certain masses. I can't remember what the exact figure is. It's somewhere around 10 to the 10 that effectively your ISCO, your inner stable circular orbit, ends up being within the event horizon of the black hole. And so you can't accrete in the kind of standard accretion disk kind of way that we've thought of before. So that potentially might have some form of influence. But yeah, that's a good question. Whether within these models that kind of thing doesn't exist, so it will keep growing. But this is kind of something to think about in future, definitely.
Morgan, and then
Yeah, so I kind of wanted to follow up on that and have you talk a little bit about maybe the black hole mass function. So, as you know, there's this troubling degeneracy between how fast the black holes grow and when they start to end up there. So, and in particular, I was thinking about if you don't limit them to an Eddington accretion rate, which we don't, as far as I know, have any evidence for. How does that shape the black hole mass function? So, for example, if you limit them, are you like damping sort of a rare tail of high mass thing? How does that?
So,
do you think we can disentangle those effects, basically, and those degeneracies?
So, potentially, I think we'll probably need better models to be able to do that, because at the moment, if I turn off, because I can just turn off the Eddington limit accretion, it effectively is still trying to input the same amount, or the amount of feedback that's 0.1 times the accretion rate in, and so suddenly you just get stuff coming in when there's gas available. It just kind of blows up immediately. And so whether that is a realistic way of what black holes would do in those situations, I'm not 100% sure. This is kind of why I want to start relaxing the assumption of Eddington accretion slightly, without kind of just letting it eat absolutely everything. The caveat, the other point I'd make about the kind of black hole mass function is that this is a single halo. So for now, this is kind of looking just at one particular beast, because these kind of masses, you need an enormous cosmological cosmological volume to be able to find halos that can host these things. And so the kind of zooms.
we have a few more questions, so let's be short in the answers so we can accommodate people. Please go ahead.
Yeah. Hi. So I didn't hear you talk about mergers as a pathway to creating these large black holes. Do you think that's just not as dominant?
It contributes, definitely, but kind of, and there are several kind of major black hole mergers within these points. I guess the black holes that have merged have also been accreting gas, so it's kind of at what point the gas is accreted, it still ends up going into this kind of same halo in the end. But it does contribute.
I was going to ask about mergers, but then I'll ask about PTA limits. Is there anything interesting, if PTA really has detected something, does that play a role in this discussion?
Potentially. I guess they're kind of for the most massive mergers, of which I think this particular halo, for example, only has kind of major mergers when it's slightly earlier on, when it's not quite as big. But potentially, you kind of need a couple of big halos like this close together that you could eventually merge and do this kind of thing. But hopefully that will be feasible, if rare, to do.
Okay, last question. Go ahead, Tony.
So these early galaxies are small, and they tend to be merging, and they tend to be chaotic. And so I've always thought that they would be eating whole stars instead of eating gas. That they would be chaotic enough that you wouldn't really have a lost cone, and whatever massive thing you've got is always spiraling into the local center, whatever that is, and so the lost cone for stars never really empties.
That is possibly a kind of another mechanism to grow black holes much quicker is by eating stars. It's not something that's included in these models because you just don't have the resolution to try and follow this. But yeah, that is a kind of an interesting thought. Well, again, yeah, the gas is available if it can get to the very center. Just purely from gas accretion, you can grow these beasts. But that, if you can help it along the way, that'll kind of be very useful.
Directly is possible above 10 to the 8 solar masses. So the very massive ones are able to do that, but Sagittarius A star cannot do that. If the sun gets within 10 Schwarzschild radii to Sagittarius star, it will get tidally disrupted, and you will get a stream of gas that will get spaghettified.
So that then it still holds.
So then it's just gas accretion after that. It's not but above 10 to the 8 solar masses, that's indeed these black holes swallow stars whole. Yeah. Okay, thank you very much, Jake.
Thank you.
You've never seen this effect.
Yes, go ahead.
Yeah, hi everyone. I'm Vadim. I'm a postdoc here, and I've changed the title of my talk because I thought that 10 minutes might be a bit too short for a talk with the word numerics in the title. So I went with a much less ambitious topic, galaxy formation. And in particular, I'll show you some insights about how our own Milky Way might have formed based on results from numerical simulations. And so this field actually got rejuvenated recently with the advent of Gaia, as new accurate astrometric data appeared for large samples of nearby stars. And now in this data, we can actually see the imprints of how our own Milky Way disk formed. And earlier this year, there was like several papers appeared pretty much back to back with each other. And it was from, there are different groups working independently, and we actually had a couple of talks in this very room from Charlie and from Vasily Belakurov, who showed some of these results. And these talks actually were like an inspiration for the work that I'll be showing. So the plot, so here these plots, they show the distribution of nearby stars, rotational velocity of nearby stars as a function of their metallicity. And we can think of metallicity as a proxy for the formation time, with the low metallicity stars formed early on, right? And then high metallicity stars formed at later times. And the lowest metallicity stars observed in these samples form this dynamically hot component with a very large scatter in the velocity and almost no net rotation. And our understanding of this, of what this feature imprints, is this really early stage of galaxy evolution, when it was really hard even to tell whether there's any single progenitor of the galaxy. And instead, stars were forming in a bunch of smaller galaxies that then merged together, creating this progenitor of the Milky Way. Then, at later times, something happens, and the distribution of stars acquire some net rotation. And this happens really rapidly. Over the change of metallicity only by a factor of 2, stars acquire most of their rotation. And this manifests the transition to this later stage of galaxy formation, which we see nowadays when all Milky Way-like galaxies are arranged in these nice disks which form stars. So and then the question is, how do we go from this mass at high redshifts to these really nice disks that we see in present days? Right? Clearly from this movies, you can see that simulations, they qualitatively capture this transition. But at the same time, there are some problems. So for example, this is a comparison of how this spin-up feature in the metallicity and kinematics of stars look like in zoom-in simulations of individual Milky Way-like galaxies. And so these different lines, they show simulations from different, the results from different suites of simulations that employ very different physics that goes into these models. But independent of these assumptions, these simulations generally predict that the formation of the Milky Way happens much later. So the spin-up occurs at the metallicities which are roughly 10 times higher than what we see in the Milky Way. And this translates to delay times of the order of a few billions of years. Right? So the question is, what's going on there, right? And there are at least two possibilities. So on the one hand, maybe we don't understand something fundamental about galaxy formation. So maybe there is some process missing that we do not include in simulations, and therefore we fail to form galaxies early enough. This is one possibility. Another possibility is that the Milky Way is just special, right? And we know that this is true in some respect because Milky Way is not a typical Milky Way mass galaxy, right? So at the very least, it's not as actively star forming as other Milky Way mass galaxies. It undergoes this weird transition being in the Green Valley. So maybe its formation history is also special. And in simulations, we can actually address the second point, right? And for this, we just need to look not at the simulations of individual galaxies, but some representative sample of the galaxies. And this can be done with cosmological volume simulation. So you may have heard about Illustris, TNG. Again, yeah, anyway, so this is like a cosmological simulations that were largely developed here. It's like state-of-the-art nowadays. And this is like a short summary of the key features of these simulations. I will not go into details. I'll just mention that here we use TNG50, which is the highest resolution version of this cosmological suite, which has relatively small box. It's the 50 moving megaparsecs on the side. But it's large enough to have some representative sample of Milky Way-like galaxies. And particularly if we select galaxies that have masses like a Milky Way, that are star-forming at redshift 0, and also have some sort of a disk, then we end up with roughly 60 galaxies that satisfy this criteria. And this is how they look like in this plane of the metallicity versus stellar rotation. So these gray lines, they show individual galaxies, and they all show this spin-up feature, right? And just like the results in the simulation that I showed before, on average, disks form later than the Milky Way. But at the same time, there are some galaxies that form early as the Milky Way. So we can do more quantitative comparison if we look at the median and 1 and 2 sigma percentiles, and we can see that the Milky Way is comfortably fitting within 2 sigma of the overall population. And in fact, if we go through each of these galaxies, we can find roughly a dozen that look almost exactly like the Milky Way, right? So overall, it tells us that Milky Way is likely just special, right? So it's special, but it's not very uncommon. So it's within 2 sigma tail of the overall galaxy population. And the physics that goes into TNG model, it's, I would say, reasonably realistic to reduce this early formation of the galaxies, right? So we can ask some questions, right? For example, we can see what's the reason why these particular galaxies form that early. So why some galaxies spin up early while other spin up much later. And in simulations, we have a luxury knowing where and when each star particle has formed, so we can look at these statistics in a space of stellar ages versus their kinematics. And here again, we can see this nice split between these different populations of early and late spin-up galaxies. And there are also interesting features. So for example, the Milky Way analogs, they form really early, within the first few billions of years of evolution, and this formation happens really rapidly. So it's a really sharp increase of the rotation velocity that happens over a time scale of order of 1 billion years, and then they just stay around. While for the late spin-up galaxies, there is a much more diversity in terms of the how sharply this spin-up occurs and when it happens. Right? to the first order, the reason why there's this difference is simply because of the mass accretion history. So if you look at how these different galaxies accumulate their mass, we see there is similar separation in the halo mass versus time. So the early spin-up galaxies, they accumulate most of their mass by within the first few billions of years of evolution, and then they just gradually grow. While the late ones, they form over much more extended periods of time, and they experience multiple major merger events that you can see as this jumps in the halo mass. So in the result, this translates directly into the formation of the Milky Way disk. So as an example, this is how the evolution of one of the early spin-up galaxies look like. So these blue lines show the statistics at redshift 0, and the colored lines show how this statistic looked like in the past. And so, for example, here in this age versus rotation velocity, you can see that this distribution was already in place early on when the disk just formed. So the disk forms at only 1 billion years after the Big Bang, and then it just stays there and continuously forms stars. And this is also evident from this movie of how this galaxy looks like edge on. So these early ones, they are, I would say, pretty boring in terms of the evolution. The lifetime of late spin-up galaxies is more eventful. So early on, they also form some sort of a disk with so this spin-up feature is very similar to what we see for the Milky Way, but later a major merger comes in like this. And it completely destroys the disk that was formed early on and resets and then another more prominent disk forms. So essentially what major mergers do, they reset the chemical and age evolution of the galaxy. So in the spin-up feature essentially tells us the timing of the last major merger. So overall, the fact that we see this feature at low metallicities in the Milky Way is consistent with what we know about the accretion history of the Milky Way that didn't experience any major mergers in the past 10 billions of years. Okay, so in the last 0 minutes, I'll quickly show some other insights from the simulation. So essentially, the question is, what physics drives the disk formation, right? And okay, I'll skip this. And one major insight that we now have is that stellar feedback might be an important factor that drives formation of galactic disks in the first place. So what outflows do, they take some gas from the interstellar medium and send it out to the halo. And thereby, they couple the momentum of the disk with the halo and create this fountain outflows that fill the entire halo and that correlate with the galaxies. It's shown here in this movie. It's an edge-on view on one of these galaxies, and the color shows the rotational velocity, red meaning that it correlates with the galaxy. And the disk growth is then supplied by the reaccretion of this material from this correlating halo. So essentially, it means that the disk feeds itself with a high angle momentum material. This is just more quantitative way to show this. So this is just a stacked version of evolution of several of these galaxies. And it shows that the star formation rate early on increases following the increase in the inflow rate. And as a result, the outflow rates also increase. And then at later times, significant fraction of the inflow material comes from the recycling of the outflow gas. And what's important is that the angular momentum of the inflowing gas, it imprints the angular momentum of outflows. And as a result, as the galaxy grows, it continues sending this high angular momentum stuff into the halo that eventually spins up the galaxy. So this is sort of a positive feedback loop. Yeah, and I'm done. I'll just leave the summary here. Yeah.
The obvious question is, we find ourselves in a galaxy that is special, right? At 2 sigma. Is there an anthropic reason for that? So is the reason we are in this unusual galaxy because if there was a major merger, the sun would be perturbed and we wouldn't exist, do you think?
We need larger sample, I guess.
Any other questions?
illumination. The FE over H curve, what is there just a one well-defined relationship between FE over H and age?
So between what?
Iron to the iron to hydrogen ratio versus time. How is that defined?
You mean how?
In other words, is there a one-to-one correspondence between age and FE over H?
No, it also reflects, it's, there's like average trend, but there's also a significant scatter depending on how enrichment happens and how accretion.
The FE over H is calculated as part of the simulation.
Yeah, so this is computed in the simulation, but there's some uncertainty in how like this yields and enrichment works. So to avoid this, we actually recalibrate the metallicity in the simulation such that their distribution match exactly what we observe at the Milky Way. So this is just to factor out this uncertainty in how enrichment works.
We need to move on because we are short on time. Let's thank the leader.
Good. Can you hear me? Thank you for inviting me. It's a pleasure to talk about some early results from JWST, in particular some work done with the JADES collaboration, and to provide a bit of an advertisement for some ongoing work, partly done at the CFA, that will soon provide much more of this kind of data. So over 2 months ago now, the early release observations of JWST were made public, and I'm sure you saw all of those images, including this one of a lensing cluster field, MaxJ0723. The publicly released imaging has been extremely exciting and has already led to a number of discoveries of redshift greater than 10 galaxy candidates and even early estimates of the UV luminosity function and stellar mass function at these early redshifts. However, at least exciting to me were the JWST spectra that were released as part of the early release observations. These spectra were obtained with the NIRSPEC instrument, which is a multi-object spectrograph using these micro-shutter arrays, operating between about 1 and 4 microns. And the early release targeted several high redshift galaxies that were identified based on HST data. This really exciting thing is that many rest frame optical emission lines were easily detected in these galaxies at redshifts greater than 6. And these include the Balmer hydrogen lines and oxygen lines, neon lines. And these lines probe the physical conditions of the ionized nebula around massive stars during the epoch of reionization. I mean, these are objects at redshift 7, 8. This is extremely exciting. Many other groups were very excited by this as well. A number of studies have already appeared on the archive analyzing the emission lines to infer properties of the ionized gas or the broadband photometry of these galaxies to infer stellar masses, estimate stellar ages, which is greatly aided just by knowing the redshift, even without looking at any of the emission line properties. Many of the high redshift galaxies showed very strong oxygen-3 emission, especially in the forbidden 4363 angstrom line, which I'll talk about a little bit more later. But one thing that hadn't been done was to combine the photometric and the spectroscopic data self-consistently and simultaneously in a model for the galaxy properties. So in a study led by Sandra Takela, a former CFA fellow, now a professor at the other Cambridge, we undertook to do that for the 3 highest redshift galaxies in this public data. With the help of many members of the JADES collaboration, which is a group of NIRCam and NIRSPEC instrument team members that are conducting a deep photometric and spectroscopic survey of the GOODS South and GOODS North regions, we compiled the imaging data and the spectroscopic measurements of the line strengths for these highest redshift galaxies. So here I'm showing in the top left panel an RGB composite of the JWST imaging in 3 of the 6 bands that were observed. The bottom left shows the NIRSPEC spectrum The continuum is very weak or undetected, so it's difficult to determine the equivalent width just from the spectrum alone. To measure photometry, we actually simultaneously modeled all of the JWST imaging with the combinations of PSF convolved Sursich profiles. And up here in the top right, I'm showing the model, data, and residual in all of the JWST bands. And we were able to get fluxes from that, but we were also able to measure sizes from this. This is a code called ForceFo that has been developed here at the CFA. This technique allows us to get half-light sizes and fluxes. The bottom right panel here is showing the SED that we get out, along with the near-cam filter transmission curves, and in gray here is a model SED that I'll talk about a little bit more. Here are the other two objects. These are at slightly lower redshift. This is redshift 7.5, whereas the other object was at redshift 8.5. They have more complicated morphologies, which might be suggestive of mergers or interactions. And all the SEDs rise towards the reddest filter, suggesting a substantial contribution to the 4-micron flux from nebular emission lines. So I'm going to talk about the SED in a little bit more detail, the SED fitting in more detail. So again, in the top here, I'm showing the broadband photometric SED in blue and the best fit model in red. The three bottom panels are showing the ratio of the observed line fluxes to the model predicted line fluxes. So these are modeled simultaneously at the same time. And overall, we're finding a good fit to both the photometry and most of the spectroscopic lines. These fits were done with the prospector code, and the model that's being used here includes a flexible star formation history, a multi-component dust attenuation model, and photoionization grids for predicting the emission lines that are tied to the stellar ionizing sources and also reflect ionization parameter and gas phase metallicity variations. Unfortunately, in the early days of this data, it's been difficult to tell exactly where the slits were located on the sky, and also there are some uncertainties in the spectrophotometric calibration. And to account for this, we introduced a nuisance factor that scales the emission line fluxes, all of them up or down by a constant factor. We found that this scale factor was always less than 1, which could indicate that there's substantial light outside the spectroscopic slit, or a large calibration error, or it could be that there is an escape of ionizing photons to the IgM, which decreases the emission line fluxes, or that those ionizing photons are lost to dust before they can ionize the hydrogen gas. We also found it necessary to mask several emission lines in the fit. These are shown in gray in these bottom panels. So most notably, oxygen 34363 was always underpredicted by our model. This is a very electron temperature sensitive line, and it may indicate that the photoionization grids we have do not fully capture the temperature structure of the ionized nebula or the ionization structure. Nevertheless, we obtained gas phase metallicities that are consistent with other methods other studies that did use these lines as direct electron temperature probes. And we also agree with other studies that infer very high ionization parameters for some of these objects. As a result of the fits, we get some estimates of the galaxy properties. So here I'm showing the inferred star formation histories for the 3 galaxies. They all appear to be quite young, and stellar masses around 10 to the 8, 10 to the 9 solar masses. And they have very little dust attenuation. The stellar masses and the ages depend somewhat on the SFH prior that is adopted. So you can get larger ages and larger stellar masses if you adopt a different kind of star formation history prior. And we also did fits both with and without the emission lines to see what changed in this beyond just fixing the redshift. And including the emission lines gives somewhat better constraints on the dust attenuation, which helps with the stellar masses and star formation histories, but we expect this will improve a lot when we can understand exactly what the slit losses are and the spectrophotometric calibration is. Here are some comparisons of the global properties of these 3 galaxies. It's difficult to draw conclusions from only 3 objects that are selected in a somewhat opaque way. But a question that we have now is why is one of these objects so much lower metallicity than the others, even though they're all at similar stellar masses? It does seem that this is the most compact object, this Galaxy 4590, and has the least clumpy morphology. So it may be that this galaxy is accreting pristine gas, and that's why it's undergoing this starburst with very young stars, while the other two with higher metallicities are going through a starburst because of interactions or mergers, something like that. But again, very early days. So I'll just leave my conclusions here and end by noting that the JADES collaboration with CFA involvement has observations scheduled this fall that's going to provide a lot more of this kind of data, but with more photometric bands and with higher signal to noise. And as of 24 hours ago, we completed our deep imaging in about 30 square arc minutes in 9 filters. And near-spec spectroscopy of hundreds of galaxies will commence in the coming weeks. A number of other programs are going to be obtaining JWST spectroscopy in the coming months, promising really exciting times ahead for these kinds of studies that combine photometry and spectroscopy. So, thank you.
Thank you, Ben. I heard from an observer, I was not on that paper, that the editor of Nature said that over the past month there were many publications of high redshift galaxies on the archive, and none can be trusted because the calibration is a big issue. And I tried to get a sense from the observers, is it really you can answer this because you have spectra as well, so what's going on with the calibration of JWST?
So the photometric calibration has been a bit uncertain. There was not a huge amount of the calibration data taken early on. That has been improved lately. There was 2 days ago, a new calibration was released, and I think people are starting to look at that more.
So how much uncertainty would you assign to all these papers on the archive in terms of their photometry?
10 to 20% on the photometry. We used 10% when doing this fitting because we knew it was early days and that these were uncertain. So the formal flux uncertainties were much less than that, but we decided to. For photometric redshifts, it can be 20% can be problematic. So it's really nice to have spectra here and just to have that redshift.
Yeah. So for the redshift determination, it could be bad, but you're saying, but for the flux, it's not so bad. I mean,
for this, so 20% might be enough to somewhat change some of the dust attenuation that we're getting, some of the UV continuum slopes and things like that. But yeah.
Other questions? Yes, go ahead.
Are any of these being looked at with ALMA?
This is in, that's a good question. I don't know. I'm not sure. That would be, I know that in the deep fields, we are definitely going to have ALMA coverage of a lot of these high redshift objects that we're about to observe. And that will be really interesting. These do have fairly low dust attenuations that we're measuring. They are selected to be pretty blue. I'd be surprised if they were extremely strong ALMA sources. But that's a good question.
I wouldn't be surprised if they were undetectable.
Yeah.
Okay, so we will all go out to take a photo, but before we do that, let's thank them.